Hello, everyone, and welcome to our third session on the Astronomy for Educators workshop. So today is our third session with Dr. Daniel Barth, and we all look forward to today's session. Over to you, Daniel.
Good morning. Good evening to you. Good morning for me here in Arkansas in the United States. It's just after dawn here, and very chilly morning. We're at about 5 below centigrade, and we are recovering in our area from a 20 centimeter snowfall. Not much in many parts of the world, but here in the southern United States, it's unusual for us. So it's been a brisk few days here. Well, I'm glad to have you all back. And once again, I would encourage everyone to download the Astronomy for Educators book. And Dr. Hassan has posted the link for you. And this is a free download. The book is published by the University of Arkansas as an open resource for all teachers, students, parents, anyone who would be interested. And I hope you will take the time and download the book and share the website with your colleagues and friends so they can also have a copy. I would also be very appreciative if you would leave a review for the book or some comments. I have an Astronomy for Educators page on Facebook now. So if you go to Facebook and you look for Astronomy for Educators, you'll find my page. It's very new. I just put it up a week or so ago. But if you have comments about this presentation, this series of lectures, or the book itself, I would be very pleased if you would leave them there. Now, last time when we met, we were discussing, among other things, our two main themes for these talks. One has been low-cost science. It's true that in all countries of the world, there are school districts where the local community struggles with funding. And it's a common perception that among teachers and administrators that it's not possible to do a high-quality STEM program if you don't have access to expensive equipment. I reject that idea. I taught in high-poverty schools and urban areas for more than 20 years. And I managed to have a high-quality STEM program, particularly in astronomy and physics, by using low-cost methodologies. The essence of the low-cost methodology is that my students were taught to build their own equipment, build their own materials. If you were with us last time, you may have made your own planetary models with us. These are made from ping pong balls, but you can make them with many other things. I had a teaching and education student this year who made her models from 2 oranges, peeled off half of the rind, and the white area underneath she colored with markers for her planetary and lunar models. And it worked just fine. The idea of low-cost methodology is that it democratizes STEM education. STEM is no longer restricted to the schools that can afford it. And there are schools around the world who work with the Astronomy for Educators textbooks and the low-cost science methodologies. The second important message for us here in this 3 lecture series is the idea of teaching English through an experience-first methodology. Schools across India, in fact, in many parts of the world, English is the language of science instruction, but many students do not speak English in their homes. If you might find it odd, but when I taught in California, in the low desert region, this was true of up to 70% of my students. They came to school, they spoke English at school, but they didn't speak English in their homes. The majority of those students spoke Spanish at home, but we also had a Russian-speaking community. We had many Asiatic languages. We had communities that spoke Korean, Vietnamese, Cantonese, Mandarin, Tagalog, many Japanese, many languages. And the interesting challenge for the educator, we had students who were conversationally fluent in English. In other words, these students could come in, they could talk with you, hello, good morning, how are you? What are we doing in class today? They could have these conversations just fine. But when it came time to open a textbook or to discuss technical materials, astronomy, physics, chemistry, then very quickly, teacher and student both realized the limits of this English language fluency. My students were often conversationally fluent, but not academically fluent. My essential methodology for this is called experience first methodology. And I believe that, I'm hoping I sent that to Dr. Hassan. If not, I will send it, the paper I did on this, to her so you can all download it. And the essence of experience first is that you allow students to do hands-on work. Essentially build their own equipment, make the experiments with the equipment they've built. Each student does this effectively in their own language in their head. My students who spoke Spanish would sit and converse in Spanish while they built their equipment, assembled their models, did their experiments. And then after they had the experience, then as a teacher, then I would teach them the vocabulary to help them become fluent and learn to express what they knew. And it's my firm belief that every student is smarter than they can express. This is a major theme in many of my education classes now that I'm at the University of Arkansas and training teachers instead of teaching science. I tell my young teachers that their job is to help students learn to be fluent in the language of the subject they are teaching, because every subject has its own language. And by giving students experiences first and then laying vocabulary over it, this is far more expedient in my experience than the traditional method, which was simply, oh, now we're going to learn vocabulary. And in classrooms in America when I was growing up, and still today, it's common for a teacher to start out, and there are a lot of languages spoken in the room, and it doesn't matter what subject they're talking about, literature, mathematics, science, social studies, doesn't matter. The teacher begins, okay, now we're going to start a new unit on Newton's laws. So the first thing, we have a long list of vocabulary terms. And of course, you're saying, here's a word and here's a bunch more words that tells you what that means. And for students who have minimal or low English fluency or low academic fluency in English, this method is simply ineffective. The experience first method works far better. And that's what we've been working on here, is showing you how to teach science, particularly astronomy and space science, with low-cost methodologies. And at the same time, learn to teach technical English in your classrooms to those students who may not speak English at home. We refer to this student who doesn't speak English at home as an ESL student, English as a second language. It's sometimes also referred to as ELL, English language learners. And we had ESL, and that was the term many students didn't like, because they didn't like being singled out and saying, oh, your English isn't very good. But I would tell all my students they were SSL, science is a second language. And so we were all going to learn to speak the language of academic science together. So let's continue and pick up where we left off last time. I'm going to see if I can successfully switch my camera here. There we go. Last time when we were here, we made a clay model of the lunar surface, and I'm hoping you were here with us for doing that. What we're going to do today is we're going to explore some map making and some mathematics that we can do with this activity. This is, I've had some teachers tell me that this activity is like an art project, and I've had secondary teachers and teachers who taught introductory astronomy at the university level say, well, goodness, that isn't an appropriate project for my classroom because it's just art, which I found rather strange. It's never just art. Art is important. We have STEM, of course, but in the United States and around the world, there are a great many teachers who refer to teaching as STEAM. They add the A for art in addition to science. And I think this is an important thing because essentially in science, when we make an hypothesis, sometimes we make an hypothesis with mathematics, sometimes with words, but often when we express a hypothesis, we're making a model. This model of the lunar surface is my hypothesis of how the lunar surface looks and how its features are organized, and it's a physical hypothesis, it's a model. So I think the artistic component of science is important for everyone. It also is important because it makes science accessible to students who might not have science as their very first choice academically. There are a great number of students who have been in my classrooms over the years who said, well, I'm here, professor, because I have to take the science course, but I don't like it very much. No offense to you, but I don't like your course already. And I always told those students, please give my class a chance. And there's fun things for everyone to do, but sometimes that message is hard to get across. What we're going to do this morning is we're going to take this model, and if you made one last week, I encourage you to get it out and work along with me. We're going to take this model and we're going to transform it from a purely artistic representation to a more mathematical representation. And what I have here, this is a rotary cutter. In the United States, when I'm doing this activity, I often use a pizza cutter, which is a common kitchen utensil here in the United States, but in fact, any knife will do. I've also seen this done where someone has taken string and stretched across and pressed the string into the model. But the idea is that we're going to make lines. So we're going to make lines of latitude and longitude. So I'm taking my cutter and I'm running across here. And this may not show up very well on your screen because of the white on white. But essentially what I'm doing is I'm taking my cutter and I'm running across here. I've got a printed scale on my desk, and I'm using the ruler and my rotary knife here, and I'm making lines horizontally as you're looking at it, and I'm going across and making a nice, neat set of lines. These are about, these lines are about 2 centimeters apart, approximately. And now I'm going to do the same thing, And I'm sure many of you are now looking at this and saying, aha, I know what he's doing. Because essentially, we have a landscape model here, and my little mountain in the crater came off. We have a landscape here, and basically what I'm doing is I'm dividing up my landscape with lines of longitude and latitude. And so as I do this, I'm going ahead and making my lines here. I hope you're following along with me on your own model. And are these lines going to be perfect? No, they're not. Are they all going to be exactly parallel? Well, yours may be, mine are not. One thing that many of my education students discuss with me in class, there we go. I've got a set of lines. Let me tilt this up and see. There you go. There you can see them. And so one thing that many of my education students express to me is they say, well, when I make this, it's not perfect, Professor. My drawing isn't as neat as yours. My clay model doesn't look as nice. And they try it with their students and they say, well, you made a model of the Earth with a ping pong ball and it looked like this, and you could see North America, South America, and I made a ping pong model and it looked like this. And I do try to tell my students, and let me emphasize to you, that the effectiveness of this model does not depend on your artistic talent, nor will it depend on your students' artistic talent. In effect, what we're doing is we're making an hypothesis, a physical hypothesis here, a physical model. And for our students, the image that they have in their head is likely much more accurate and perfect than the model that they're actually physically creating. But in terms of its utility for teaching science, that's unimportant. The artistic quality is not a concern. And if you have students who are struggling and say, oh, my model isn't pretty, this isn't very good, it's important to emphasize to these students that this is a physical hypothesis and that the artistic merit is not crucial. So once we have a linear scale here, one of the interesting things we can do from here is we can go ahead and we can make a map. I'm going to go ahead and set my model down. As you can see, I've already drawn a grid here, and this is, I think I drew it a little longer. It's 7 squares by 6. My model here is effectively 6 by 6, so we'll ignore this piece. And at this point, I tell my students, okay, it's time to make a map. And I get a lot of groaning. Oh, no, I can't draw. I can't make a map. But the nice thing about latitude and longitude lines is that it makes the map very easy to draw, because essentially the map gives us reference points. There was an old paper and pencil puzzle that was quite popular when I was a boy. It would show squares, and they would give you an empty square diagram and then a set of scrambled squares, and each square would show you what to draw, and they would be labeled. And so you would go ahead and you would recreate on your grid what was shown on the squares, and when you did it right and organized everything, you got a picture. So I'm going to look at this. Let's see how well we can do. I'm going to look first at this Maria area. And as I look at my Maria and I see that, and again, I'm going to disregard these squares because I made my grid a little bit too big. I can see that this starts coming across here like so. And it cuts across and up into the next one and comes over and comes down a little bit like this. And then it comes out again and it comes down for about 2. And it comes around here. And so I've drawn my Maria, and I think you can maybe look here and see the shape with the little indentation here. And I'm just trying to go ahead, and I see that I have a series of mountains here. So I'm just going to draw some little symbols for mountains. And now I can go ahead and start to draw my craters, and I see I'm going to start by drawing my larger craters, and I simply go ahead and look and say, well, what circle is, or what square is that in, and how big is it relative to the square? And I can go ahead and I can start, and I'm going to just work very quickly. I can start working here. If I see, oh, I've got a couple of smaller craters here, and by working diligently and patiently, I can find that I can go ahead and trace out my craters. And I've got one down off here that's quite large, and there's a mountain in the center. I've also got another one down here that's quite large, and there's a mountain in the center. There's some that are shallower. These are referred to as eroded craters. They're generally much older than other crater features, and so I'm not going to draw everything here, but I'll draw a few. We've got a crater chain here, and so I'm looking at various features. And I've got an eroded crater up here. And so very quickly, I have a representation. We've drawn a map. So once we've drawn our map, then the next thing we want to investigate, and excuse me, because of the orientation, I'm drawing sideways here, so I'm hoping that this is clear to you. We have to set up a scale for our map, and for our scale, we just go ahead and we set up one square is equal to, and we have to come up with an idea. How big is this? Well, if we apply a little knowledge, I know that a Maria on the moon is typically 300 to 500 kilometers. So I'm going to look at this and say, oh, this covers almost 4 squares across and 3.5. So I'm going to say 1 square is equal to 100 kilometers. Now I have a scale. And again, you will excuse my sideways penmanship. It's not the best. So I've set up a scale. And in fact, you can set a scale for anything you would like. And once I have a scale, now that I'm measuring and I said, well, my squares here, okay, I've drawn this a little bit differently. 1 square is 2.5 centimeters. And so I can say, oh, 1 square is 100 kilometers, and that's also 2.5 centimeters. So now that I have this information, now I can take my ruler and I can measure anything I like. And so I'm going to measure a small crater here, and I see this is about 1.3 centimeters. And so now I can set up a simple ratio, and I can say, oh, how much is 1.3 centimeters? Well, 1.3 centimeters is to 2.5 centimeters as our unknown distance x is to 100 kilometers. And if I go ahead and I'm sorry I don't do that sort of algebra in my head, not anymore anyway. And so if I do this, I multiply across, and so I get 1,300 divided by 2.5. And so I get, this comes out to be, my unknown comes out to be 52 kilometers. So this crater that I'm shading in here, I measured it, and I simply did my ratio, and I said, well, if this square is 100 kilometers, this crater comes out to be 52. And this puts our arithmetic and our algebra and our ratios on a very practical basis. One interesting thing, one thing that bothers me a great deal in the United States, and I have no knowledge of how other countries teach mathematics, but one thing that bothers me very much is that in the United States, we teach mathematics in a very unrealistic fashion. It's often completely disconnected from everyday life. And so in a mathematics textbook in the United States, you might see something like Johnny has 3 tea apples and 2.5 Y friends. And if he wishes to distribute this equally, how many apples will each friend get? And you're like, nobody talks like that. No one says, I have 3 tea apples or I have 2.5 Y friends. No one says anything like that. And so the mathematics and the descriptive problems, they seem very odd. And students look at them and say, this is strange. I don't understand this. I was talking to a teacher online this morning, and they had a physics problem, and I'm going to draw it for you very briefly. And they had a physics problem this way, and the physics problem looks something like this. And they had a graph where distance increased this way and time increased this way. And this was supposed to be a graph of a ball which was falling. And they said, I don't understand this. And I said, well, part of the reason you don't understand it is because nothing falls up. I said, who wrote this? They said, oh, it was a problem they saw on a praxis examination, which is an examination for educators. And I said, well, this is terrible. And the reason you don't understand it is because you shouldn't draw a picture of a ball falling this way. You should go ahead and draw a picture of a ball falling this way, where essentially, in this case, time goes here, and the distance falling is negative. I said, oh, what ball falls up? It doesn't. A ball goes here, and it goes farther downwards. In other words, G, I said, is equal to negative 9.81 meters per second squared. And I said, this is a negative number because falling occurs downward. And so now you can understand that at any given time, the slope of the line gives you your instantaneous velocity. And as the slope increases, the rate of change becomes the acceleration. So G here is the rate of change. And this is a parabolic curve. And of course it goes down because everything falls downward. And at that point, the teacher said, this makes much more sense. I was very confused because they drew this and I'm looking at this saying, well, how does the ball go up? And of course, the way we graph doesn't necessarily have to have a connection to physical reality. But if we're asking children to understand science as we present it to them, I very firmly believe that we do a better job as teachers when our presentations adhere closely to the reality that the child experiences from day to day. And this is an important thing. So, coming back to our experiment here, we see that, now we have a situation where a student can make a physical measurement. I'm going to measure the distance across the Maria. And then they can do a conversion and they can say, I see. This is how many centimeters this feature is on my map, and this is how many kilometers wide the feature is in reality. And this is the way maps work in actuality. The one interesting thing that I notice is that most of the electronic maps that students use on smartphones, for instance, when we get a map, here's a map. It probably doesn't show up very well. But when you take a smartphone and you say, or a computer, and you say, let's use Google Maps, and there's almost never a scale on these maps. It was a standard feature when I was learning in school that every map had a scale, and you could take your ruler and the scale would give you an idea that matched physical reality to the image on paper. Now, of course, with electronic maps, whether they're on a computer screen or a phone, you can stretch them, right? You can, with a phone, you take your two fingers and you stretch the map or you squeeze it and bring it in. But it rarely shows a scale anymore. I think this is a deficiency because students need to be able to look at a map and say, if this is 300 kilometers, then this must be about 100 kilometers. And they should know how far that is in reality. How long would it take me to travel by car, 100 kilometers? How long would it take me to walk or bicycle, 10 kilometers? And look at a map and make a connection to their real life. One of the things we can also do in this case with a map like this is we can look at 2 points. We can say, okay, let's take 2 points and we're going to take, and I'm going to try to draw in a different color. I hope that it will come out right here. Maybe, maybe not. Let's take a look at a distance between 2 craters. One here, the center of a crater. Let me see if I can move this a little closer, make it easier for you to see. And let's pick another crater down here. And we say, how far is that? Well, certainly one thing we can do is we can take our ruler and we can measure the distance directly, but we can also go ahead and use our coordinate system in another way. And so we can draw. Here we are. And what have we created? Of course, we've created an equilateral triangle. And this allows us to use the Pythagorean theorem. So if we say, well, this is side A and this is side B, we know the Pythagorean theorem tells us that A squared plus B squared will give us c squared. And so we can say that the distance between the 2 points C is equal to the square root of a squared plus b squared. And so this lovely Pythagorean theorem, this is also sometimes referred to in algebra as the distance formula. Sorry about my penmanship. The distance formula. And students see this and they're given problems with graphs. And here's two coordinates on a graph. And okay, we have coordinates, and let's consider this to be the x-axis, and let's consider this to be the y-axis. And if this is the x-axis and the y-axis, we can now take physical locations and establish coordinates. And so if this is our origin point down here, then we can say, oh, well, this coordinate has an x of 0.25, and it has a y coordinate of 0.75, and this coordinate has an x of 3.1, and it has a y coordinate of approximately 4.5. And so we can say, we can establish coordinates here, but we can also treat these x and y coordinates as latitude and longitude points. You could say, all right, every square is 5 degrees. You could say each is 5 degrees. So what's the latitude and longitude? So once again, this simple exercise, making a model in clay and then making a map, you can introduce all sorts of algebraic calculations in practical cartography. And if you have any sort of a globe, it's fairly easy to determine on the Earth how far is 1 degree. And I know the Earth has a circumference of approximately 40,000 kilometers. And so if we have 40,000 kilometers and we divide by 360, that means each degree is about 1,100 or 111 kilometers. Well, what is it on the moon? Now we bring home the idea that other worlds are different than the Earth. One of the interesting things about studying astronomy, many of my students had this idea that all worlds were essentially Earth-like, which of course is not at all true. And how do we bring this idea home to them? One interesting way is to say, well, let's consider the moon as a world, and on the Earth, we know 1 degree takes us about 111 kilometers. How far is it on the moon? Well, the moon has a diameter of about 3,500 kilometers, so that gives it a radius of about 1,750 kilometers, and of course, the circumference is 2 pi r, which means the moon has a circumference of approximately 11,000 kilometers. And if you divide that by 360, that means a degree on the moon is only about 30.5 kilometers. So 1 degree is equal to about 30.5 kilometers. And so you can use the moon's physical geography to establish a scale. If you say, oh, this is 5 kilometers, then 5 times 30 gives us about, we picked a random number here, about 150, about 100 kilometers. But if we're using this as a true map of the moon, then effectively each degree becomes, or each square becomes about 150 kilometers. So you can take this map, you can relate it to the physical geography of the moon. You can use this as a comparison between the moon and the Earth. One of the interesting things that I find is that many students don't really have a good idea of how big the moon is compared to the Earth, nor do they have a solid idea about how far the moon is away. If you're using a ping pong ball model of the moon, and I have one right here that we made last week. If you have a ping pong ball model of the moon like this, then essentially the Earth's diameter is about 4 times this size. And I think I have here in my office. Yes. I never seem to have everything at hand. Here's a ball which is essentially 4 times bigger. And if we look at the diameters, this is about the right scale for the Earth and the moon. Wow, that's quite a difference. Most people don't picture the moon as being that small. And so how far away would it be? Well, this is just a child's play ball, and this is about 15 centimeters in diameter. And if this is 15 centimeters in diameter, the moon is approximately 30 diameters away. So we would take our 15 centimeters, multiply by 30, and so, oh, that's 4.5 meters. So we can take some string and stretch out 4.5 meters. And if we stretch out 4.5 meters, and then we use the Earth as the center, then we get a circumference of 9 meters, or we get a diameter of 9 meters. And so we take this 4.5 meter string and we attach our ping pong ball on one end and our vinyl ball on the other. And if you don't have a vinyl ball of the right size, you could cut out a square of cardboard or construction paper and represent the Earth. That's fine. Go ahead and we would go out typically on the play area where it's paved, and we would go ahead and take some chalk and draw on the ground, or go out where it was dirt and draw in with a stick in the dirt and draw out. If you're on an area which is turf, you can take and make little flags with pencils and some construction paper, and you can mark out how big is the orbit of the moon compared to the size of the moon. And if you think about a ping pong ball in a 9 meter wide circle, you start to realize, wow, space is really large. The moon is very far away. And compared to the size of its orbit, it really is just a very small body. This also gives students the idea. We say, okay, if the Earth is, say the Earth is 30 centimeters, that's about the size of a typical football, soccer ball in the United States, football in India. And you say, okay, 30 times that. And so you have 30 centimeters, 30 times, and gee, that comes out to be a 9 meter radius. And so you say, gee, I have an 18 meter circle. And sometimes I've told students, okay, we have our soccer ball, and for the moon at that size, a baseball makes a good comparison. And we say, okay, stand in the center of the circle and make a paper airplane and see if you can hit the baseball 9 meters away. And wow, that's really hard. And you get the idea, oh, flying a spacecraft from here to here. One of the reasons most students have serious misconceptions about the size of the lunar orbit and the size of the moon compared to the Earth and anything else is, of course, the way we do textbooks. Because if we have a textbook and we say, oh, gee, let's go ahead and have a textbook page, and here's our textbook page right here, and we say, gee, this is a textbook for science, and we want to draw the Earth and the moon, and so here's the Earth right here, and we draw over here just a little smaller, and we say, this is the moon. And we have to fit the illustration on one page. And because we have to fit the illustration on one page, we distort things. We distort the size of the Earth compared to the size of the moon, and we very seriously distort the distance between them because of our need to fit this on a physical page. And doing it on the computer screen is no better. The computer screen is just as limited. And if we were to draw the actual size, relatively speaking, of the Earth and the moon, and we wanted a real drawing, if we wanted to go corner to corner here, then we would have the Earth would be a very small object, and the moon would be a point in the other corner. And if you're saying, gee, I can't really see that, Professor, well, that's because if we drew an actual model, they wouldn't show any features. The diagram wouldn't be recognizable. It's often very instructive to teach scale. One of the things we teach very badly, at least in the United States and in most science textbooks that I have seen, is we are very poor at teaching scale. We do not teach accurately the size of things compared to one another, nor do we teach accurately the distances of things one to another. One interesting way you can do this, and this requires you to be outside, you can't do this in a classroom, is to start out with a 30 centimeter ball. An American basketball is about this size. A 30 centimeter ball, and say, this is the sun. Well, if a 30 centimeter ball is the sun, then Jupiter is about the size of a ping pong ball. The Earth is about the size of a small pea. Mars is a very small bead. Worlds like Pluto, this is a grain of sand. And you say, okay, if the sun is 30 centimeters, how far away is the Earth? Turns out the Earth is about 39 meters away. So if you go ahead and you start walking and you make the assumption an adult's single step is 1 meter, sometimes I've seen these devices where it has a wheel on a stick, and each time the wheel revolves, it's 1 meter, but you can do steps, and oftentimes with a smartphone, you can find a pedometer application which will count your steps. And so 10 steps away is Mercury. About 18 steps, and I'm doing this from memory, so forgive me if I get this a little bit incorrect. About 18 or 20 steps away is Venus. The Earth is about 39 steps away. Mars is about Mars is approximately 52 or 3 steps away. Jupiter, now you're out to about 250 meters away. Saturn is about 500 meters away. Uranus is about 780 meters away. You get to Neptune. To get for the 30 centimeter sun to get out past Neptune is a kilometer. And it's interesting to have students stand and hold a model. Oh, this is Jupiter. Okay, it's 500, it's half a kilometer away from where the sun is. And you take the students on a walk out to the solar system, and you give each student a model and a sign, and you say, okay, hold this up. Everyone walks all the way back. This is a very healthy activity. Everyone gets lots of exercise. You walk all the way back to the sun, and then you say, okay, Earth, hold up your model, and the Earth person holds up a little pea. Oftentimes we would use golf tee, and we would glue the model to this because it's very small, or with the very small beads, we glue it on the point. And so we would have a small bead on the point, a little red bead. And Mars person, who's 50 meters away, hold your model and your sign up. Can you all see that? Everyone would say, no, I can't see that. Okay, try it with a binocular. Can you see it now? Okay. When we get out to Saturn and Jupiter, can you see them? No. You actually have to set up a telescope and mount the model of your planet on a tripod and say, okay, here's my model of Jupiter on a tripod, and it's sticking up here, and people actually standing at the Earth position. Now, take a small telescope and look at Jupiter. Oh, well, I can't see the surface details very well. Oh, really? Why not? It's too far away. Well, what about Saturn? What about Uranus? What about Neptune? And so they start to get a real idea of the scale of things. And so this is very important, and it's something that most textbooks do badly. And when we take our lovely activity here, where we have our clay model of the moon, and we have created a diagram, a map of that, and then we have done activities where we've said, oh, gee, look here. Now we can apply our mathematics in a practical way. And once we do this, we can start to take a look at features on the moon. And you can take photographs of the moon, make actual maps, make actual scale maps. You can make sketches from the telescope eyepiece. And these are important skills. But more importantly, once we take the time to do a model in clay with various features, and we say, oh, here is a Maria. Here's a crater with a central mount. Maybe if I tip this, it's a little easier to see. This is a ray system. This is ejecta. This is a lava flow into a crater. And then we go ahead and look at an actual view through the eyepiece of a telescope. Now, students who have prepared by making models of the surface, and this isn't made off of a photograph or anything else. This is completely imaginary, but the features are real. And now a student will look and say, I see a mountain in the middle of a crater. Look there at 10 o'clock, halfway down from the center of the field. And you look and say, yes, you've discovered a mountain inside of a crater. Very good. Can anyone find ejecta? Oh, I see a crater and it looks like it has splash marks around it. Oh, very good. That's ejecta material. Oh, look, this one, the lines of the ejecta are very long. That's a ray system. Oh, some craters are on top of other craters. This gives us a timeline. Older craters are more worn, and older craters are underneath. The craters that are on top, the craters with shiny ejecta patterns, these are newer craters. And so now, because the student brings knowledge to the telescope eyepiece, they take much more away with them. And it is no longer simply one more image. because students are flooded with images. Television, tablets, computers, phones, thousands and thousands and thousands of images every day. So you show them a telescope, they put their eye up, oh, it's another image. But once we create a model and we draw a map and we have scale and we've measured, and now we have latitude and longitude, and now we've compared the idea of the size of the world one to the other, from the Earth to the moon. A degree is only this much, 30 kilometers on the moon, where it's about 110 on Earth. Oh, wow, that's different. So now we get this idea. We've put geometry on a physical footing. We've put cartography on a physical footing. We've put some of the algebra and calculations on a physical footing. And now when we've done all these things, and we have an opportunity to look at the moon through a pair of binoculars or a telescope, now because we bring information to the activity, when we do have the opportunity to use real equipment and we bring more information to the activity, it becomes a vastly richer experience for the student. They take a lot more away after the activity is over. It's not just, oh yeah, I looked at it, I saw it, it was the moon. Yeah, some of the places were dark and some of them were light. So what? That's like black and white TV. My grandma has that, you know. So this map making and cartography makes all of our interesting experiences more fun. Let's go ahead and take another idea we can take a look at, and I'm going to rotate this, and hopefully this is close enough that we can see this. We've talked about measuring distances. We can also go ahead and measure areas. How do we measure areas? Well, if we look at this and we can say, gee, each square is, if the scale is 100 kilometers per square, we can say each square is 100 square kilometers. So how many squares does our Maria fill up completely? Well, here's 1, 2, 3, 4, 5, 6. Okay, well, that's 600 square kilometers. And now we can make estimations. How much of this square? Oh, well, perhaps 30%. That's another 30 square kilometers. What about this one? Perhaps 75%. This one, perhaps 80%. And so we can go ahead and systematically add up. Those of you who are mathematicians are going to immediately recognize, oh, we could, if we knew the curve, we could do an integral. But there are also other sophisticated measures for measuring areas. But in each case, we can use the theory of limits here, and we could say, let's subdivide our square into smaller pieces. And so if I subdivide a square here, and the more pieces into which I cut it, and I'm freehanding this, so pardon me if this isn't terribly accurate, but the farther down I subdivide, and I'm hoping you can see what I've done here, the farther down you subdivide, the more accurate your counting becomes. Is this not the theory of limits? Right? As the limit becomes smaller, our calculated value approaches the actual value. Let's try another way. Let's say we wanted to measure the perimeter of this Maria. Well, I'm going to start out, and I'm using sewing pins here. And so I have 1, 2, I'm trying to do this without stabbing myself. 3, 4, 5. So I've used 5 pins. 1, 2, 3, 4, 5. And I'm going to take one of these pins, and I'm going to try to do this again without stabbing myself. I've taken a pin and I've shoved the pin through a string, and I'm going to go ahead here. Can I measure the perimeter. Yes, I can measure the perimeter. Let's get around all 5 pins. Here we are. 1, 2, 3, 4, 5, and I've got this measured. And this works well if your clay model is on top of a piece of cardboard because the pins will be more sturdy. But I can say, okay, I've got this distance now, and I can unwrap it, and I can go ahead and I can take my ruler, and my ruler says, oh, my perimeter around these 5 pins is 25.5 centimeters. Now, at this point, the teacher is smiling and saying, so that's right, isn't it, students? Isn't that correct? And it won't take very long, and some clever student will say, oh, but teacher, your string in various places here, it cuts across the Maria, and it's not following the perimeter very well. The length of the string is not the same. Oh, is that right? It's not accurate? So how should we change this? And it won't take your students very long to say, well, perhaps if you added some more pins, and here where it dents in, that's a place where it's very irregular. So that's an important place to have a pin. And here's an area with some mountains where there's also an indentation. So let's put a pin here. And here's another place where we get another feature. And so let's put pins at some more important features. And now sometimes the string goes on the outside of the pin. Sometimes it travels on the inside of the pin. It depends on the contour. And now we wrap around and we say, now students, and again, I can tilt this up so you can see it. Now students, do we have a more accurate circumference for this or perimeter area, a length for the Maria? And the students will agree, yes, this is more accurate. Is it good enough? And it won't take long before your students are saying, no, the more pins we have, the more accurate our diagram becomes. And so at that point, you can say to your students, oh, well, here's how we write that in mathematics, of course. We say, as the limit approaches 0, then and you go ahead and you finish your statement. And so what you've now introduced to the students is the idea of limits. So you've taken a very complex concept in mathematics, derivative calculus and limits, and you've delivered it to the student in a very nice, compact, and unique way. It becomes not just intellectual or an exercise in the imagination, but now you've made this a physical reality. Again, if you think back to when you were taught calculus, I remember struggling with this as a student. And I don't get it. Why do we have to make the limits smaller? And my instructor would do things with graphs and various things. And it took me quite a long time. And I understood the process of how to do calculations with limits long before I understood the concept of the limit in mathematics. And so I had this odd situation where I understood the process, but I didn't understand the concept. This is very much like giving a student a set of mechanical parts and saying, assemble this in this order. Bolt this piece to this piece, weld this piece here. And the student says, but what am I making? And you say, well, it's not important. Just follow the procedure. There. And at the end, maybe you have something useful. Maybe you have a box. Maybe you have a tool like a wrench, or maybe you have a bicycle. But the student is expected to follow the instructions, even though they don't know what the outcome should be, and they don't understand conceptually the process they are engaging in. This is one of the primary conceptual pedagogical failures in teaching science and mathematics in many cases, in many schools, and not just in America, but around the world. This idea that if we understand the content, we need not understand the concept as long as we understand the process. Certainly, we teach mathematics that way all the time. You don't need to understand the application. You don't need to understand the concept. You simply need to memorize the process. A derivative is done this way. Multiplication is done this way. Division is this way. Factoring a polynomial is done this way. But what's it for? What does it mean? And frankly, as a young student, I was often in trouble with the instructor, because the instructor would say, here's our process. Today we're multiplying polynomials. And I said, well, what is a polynomial? Well, it's 3x plus 2y in brackets. And I said, well, that's nice, but what does it mean? What is it for? Who uses this stuff? Who uses this for a job? What's the application? And very, very often, my instructors didn't know. They had simply studied mathematics as a process. They had no idea about the application. And I would criticize them. Well, you don't know. You aren't very smart, are you? You don't understand what this is applied for. Later on in chemistry, I found, when you're doing reaction rates and stuff, here's your multiplying polynomials, here's factoring, here's lots of things. But I learned about the mathematics perhaps in 6th or 7th grade, 6th or 7th year, but I was in the 10th or 11th year of school before I came across an actual application for these things. I was in school an indifferent student of mathematics until at about the 9th grade. I had my first real physics class, and at that point it was a complete revelation to me. I said, oh wow, this is amazing. It's not just a parabola. This is now the path of a ball falling through the air. If I fire a bullet or throw a baseball or a rock, it doesn't matter. You have this lovely parabolic curve, and it's not just about the mathematics of parabolas, but it's about distance and height and time and gravitation. And the parabola has a physical reality. I would have been so happy as a young student in my mathematics class if my teacher had said, we're studying parabolas today. Parabolas teach us how things fall. And when we want to teach about gravitation, we also have another prejudice. We always teach gravitation as 9.81 meters per second squared is the acceleration of gravity. But it's not universally. That's the acceleration of gravitation on the Earth. If we're talking about the moon, what's the acceleration of gravity on the moon? It's approximately 1.6 meters per second squared. Well, goodness, how do I simulate that? How do I show a student that acceleration of gravity? Well, it's a relatively simple calculation to figure out that you need a ramp of only about 10 or 11 degrees to show you what the acceleration of gravity looks like on the moon compared to on the Earth. And so you can use a ramp, and if you take the ramp and you tilt it so that, I'm looking straight down the camera, and I say, gee, here's something falling, and why does it go so slowly across the field? Well, that's because it's on a very low slope, but it could also be because it's on the moon. If I start here and I roll my ball sideways, I say, no matter how fast or how slowly I roll, you tell the students every path is a parabola. How do you prove this? Well, it's relatively easy. If you have a flat board and you cover it with a nice clean sheet of paper, and then you draw a grid, and you launch the marble horizontally, you will find that, oh, it's a parabola. How do you prove it? Take your glass marble, and I would take and rub it with some sandpaper, make it a little bit rough, dip it in some ink or paint, and when you launch it horizontally, you'll get this lovely diagram. And I'm not going to do it with ink or paint this morning because it's very messy, and I'm dressed nicely for this presentation in shirt and tie, and my wife would not appreciate if I came back downstairs and said, oh, gee, honey, I have ink and paint all over my clothing. But if we have our diagram here, and of course we can set up lines that go across the page horizontally this way. And I'm going to draw this very quickly. I'm not measuring, I'm not being precise. Of course, you as a teacher in the classroom would have all of your students do this very precisely. But you make a grid, and we also make parallel lines this way. Now we have this lovely grid. I'm just going to draw very quickly here. Now, let's assume that our marble is going to be launched horizontally. Our slope, we are higher on this end than here. We're going to launch our marble horizontally. And of course, our marble is going to trace for us a very nice parabola like this. Well, if we're doing that, we can essentially count when we're launching a marble horizontally. We know the slope runs downward this way. There is no slope this way, so that each mark represents a unit of time. And I'm hoping I'm drawing all these correctly. By drawing something backwards, you'll excuse me because so each of these represents a unit of time. Let's call it a tick, doesn't matter. Now I can look at my diagram here and I can start doing some analysis. And I can say, gee, at the 0 point here, after one tick here, how far did we fall? And we've got a distance. We can see right here, this is how far we fell. And so we can measure the change in height, and this gives us the change in time. Well, we go down, what about the third unit of time? We start here, we end here. Now we see that our distance that we've fallen, our delta H becomes greater. And so if we chart this and we say, gee, here's our time, 1, 2, 3, 4, etc. And here's our horizontal position. Our first horizontal position, our horizontal positions are all the same, 1, 2, 3, 4. And what's our change in height? So when we do this, what we're getting by measuring the change in height and the change in time, we're finding that we're getting, gee, isn't isn't delta H over delta T, isn't this my velocity? Certainly it is. And so what I have now is I realize, oh, I can measure each square and determine the velocity. It doesn't take long for me to say, oh, that velocity is actually the slope. Oh, slope is equal to velocity, but I can measure it with delta H and delta T. That's what slope is. And so now I can measure the difference in slope. And so what is the change in velocity over the change in time? Well, that is equal to my acceleration. And so now I realize, oh, what am I doing simply by measuring? I'm measuring the first derivative with respect to position, the second derivative with respect to position over time. I'm actually measuring instantaneous and average velocities. I'm measuring acceleration. And once again, I'm doing calculus. I'm doing derivative calculus. And all I've needed to teach this is a flat board that I set up as a ramp and a marble and some ink or paint. And, oh, what happens now if I change the slope of the board? Well, if I make the board steeper, I get a parabola which is greater. If I make the board less steep, I get a parabola which is shallower. Well, if this parabola represents the Earth, here's the moon. This might be Jupiter. So I can, if that's Jupiter, I can go ahead and I can, by changing the angle of the ramp, I can see the vertical acceleration is greater, and I can bring home the idea to my astronomy students that different planets have different masses, different radiuses. This gives us different local gravitational acceleration on the surface. What would it be like on Earth, on Venus, on Mars, on the moon? What would it be like to play football on the moon? Well, if you can kick a football 35 meters on Earth, with the moon, even if you had an indoor stadium with air, you can count on kicking roughly 6 times farther because the gravity is 1/6 as great. So your soccer stadium, instead of being about 100 meters long, would need to be at least 600 meters long. And to cover that much ground, you would need more players because the regular regulation 5 soccer players wouldn't be able to cover that much ground. The stadium is now more than half the field. The pitch is now more than half a kilometer. And so gravitation, which is local, and we have this bias, this prejudice, that gravitation is always the same, 9.81 meters per second squared. And we always teach it that way. And of course, in astronomy, we learned that not all planets are alike. Different planets have different gravitations. And so with these ideas, we can make these subjects very concrete for our students. We can make them observational. We can make them concepts which they can see and experiment with. Well, what's it like if this is the Earth? Oh, tilted up more steeply. Wow, that's like Jupiter. Look how fast that falls. A very low angle. Oh, the marble barely curves at all. This would be like the moon. Well, what would it be like on an asteroid, like Ryugu, right? They had those samples returned from the asteroid. Well, that would be almost flat across because the microgravity is so small, it would almost not curve at all. And so we can make all these concepts very nice and very simple for our students to understand. Let's go ahead and try one more thing. And I'm going to go ahead and I'm going to take, this is a piece of construction paper that's roughly 60 by 45 centimeters. It's 2 foot by 1 foot for my friends in the United States. And so if I take this piece of paper, one of the interesting things, if we have the moon and we say to students, and we're telling them now, right? The authors always say, show, don't tell. Good teachers do the same thing. And we say, well, the moon orbits the Earth in 28 days, approximately. So we say, oh, the moon goes around once in 28 days. And we say, if you're looking down from the northern hemisphere, the moon orbits anti-clockwise. And so the moon actually orbits from the west to the east. But the student says, well, gee, but at night I see the moon move across the sky from east to west as it sinks below the horizon in the evening. So how do I reconcile these things? How can I have my students with low-cost methods actually examine and explore both the rotation of the Earth and the orbit of the moon itself? It's relatively easy to do, and all you need is a compass and a protractor. So if we go ahead and I'm going to draw some simple lines here. And so I'm going to basically draw a graph. Once again, our old friend graphing data. And so I'm going to draw a couple of lines. And this vertical line here is going to represent altitude, and this line down here, I think I drew my Z backwards. There's azimuth, and so I've got altitude and azimuth. The azimuth is compass degrees, and so if this is my due south, 180 degrees, and I'm measuring over here, this is farther to the east, and how much you're going to measure depends. You need probably about 90 degrees. So if this is 180, then this over here becomes 270. And this would be approximately 90 degrees. And so these are compass bearings, if we take a look at our compass. And so let's explore what happens with the moon over the course of a single evening. Let's say that we go out at the first quarter moon, and we see that the moon is quite high here, directly in the south, and we're looking and we're seeing that the moon right now, it's a nice circle, and this half is dark and this half is light. And we go ahead and we record this. Let's say that this is 6 p.m. Well, we've measured with a protractor, and let's say that this is 45 degrees. And so we measure our moon and we plot it. Well, we go out again and we look at 6 p.m. What's happened? The moon hasn't changed shape, but the orientation, if we're observing very carefully, the orientation of the face has changed a bit, and we can go ahead and we can measure the path of the moon as it declines in the west, and it's going to decline and it's going to move down on a fairly smooth pathway. And so we can go, oh, here's the path of the moon, and by calculating, we can calculate in degrees per hour. How fast does the moon move? And we're thinking about this, and what are we actually measuring? We are actually measuring Earth's rotation. Because the moon takes 28 days, and so if we think about this, our hypothesis is this should equal 15 degrees per hour. Do the calculation, 360 degrees, 24 hours. It comes out 15 degrees per hour. But we will find that when we actually do the measurement, our answer will not be the same. Our answer will not be 15 degrees per hour. Matter of fact, we will find that the answer will consistently be less. Why is this true? Well, the moon is not at rest in space as the Earth rotates underneath it. The moon actually has an orbital motion in the opposite direction. We see the moon sinking into the west, but in fact, the moon is orbiting to the east. So in fact, it seems to travel a smaller distance than 15 degrees each hour. Wow. And so from the difference, you should actually be able to carry out a calculation and find the moon's eastward orbital velocity. That may be difficult for some students. So let's see if we can measure the moon's orbit directly. So we make the same sort of a graph. And once again, we have azimuth on one side, altitude on the other. And let's say, once again, 180 degrees due south. And over here, we will have 270 degrees in the west and 90 degrees in the east. And let's start just after new moon. So just after new moon, and we will find a position over here, and we will get a very thin crescent moon. And then we measure this at, say, each night. Let's say we measure this at, it's the winter time now, so we measure this each night at 6 p.m. It's important that we measure each night at the same time. Well, what happens the next night at 6 p.m.? Well, the next night, our moon is now a little further, and the crescent is a little bit thicker. And a couple of nights later, we get a chance to measure again. Maybe there are clouds, and we get now the crescent is quite thick, and the moon is climbing. And now we find out that a few days later, the moon is almost in the due south. And now we have reached the first quarter phase, and the moon continues to ascend and get higher in the sky until this point, and now it starts to decline again. It starts to get lower, and now we have a gibbous moon, which is looking this way. And finally, we see that we get this lovely curved path across the sky. And by measuring the altitude and azimuth position, we know that this from position 1 to position 7 is 7 days. So if we have 7 days in that circumstance, then we can calculate once again degrees, not per hour this time, sorry, degrees per day. And so this time, instead of measuring the Earth's rotation, this time we are measuring the moon's orbital motion. And so now what we have is we have this lovely circumstance where a student with a protractor and a magnetic compass has now measured both the moon's orbital motion around the Earth as well as the influence of the Earth's rotation, which shows the moon's apparent motion in the sky in one night. So these kind of activities can give students an appreciation. And we talk about so often things like orbits, gravitation, motion, velocity. Oh, can you calculate the velocity here? Yes, of course you can, because we know how far away the moon is. And so we can calculate the circumference of that circle. What's the moon's velocity in orbit? It's really quite large. And what's the orbit, or what's the rotation of the Earth? There's another activity where you can actually measure the moon, and this one requires a video camera, but you can actually measure the moon rising above you can take a fixed surface, just a piece of cardboard, something like that, and you can measure the moon on video rising above your fixed surface, and you can time that on video, and then you can get the moon's apparent diameter from an ephemeris. You can work out the moon's motion, and from this video evidence you can calculate the Earth's rotational rate. And my experience is you can get it within a few seconds. We typically would get it within between 5 and 15 seconds doing this activity. So there are all sorts of fascinating activities that you can do using low-cost methodology, which makes these things that we often teach so badly, things like scale, orbital sizes, orbital motion. And we can say, well, that's very far away in space. So all we can do is we can have a YouTube video or we can have a textbook diagram, but that's really not true. Because when we have students make their own models, and they need not be expensive, they can be very inexpensive. If you look at catalogs that sell scientific equipment, these sorts of things are, I'm not sure what they are where you are teaching, but in the United States, models like this to demonstrate things like this, hundreds and hundreds of dollars. Very, very expensive. So expensive that you would say to the student, oh, don't touch that. Do you know how expensive that is? You can't play with that. Well, when we make our models with ping pong balls and bottle caps, and we make our observations with a magnetic compass and a protractor, we can, in fact, tell the student, do the investigation yourself. Find the concept yourself. Do the measurements. Make this a practical application. Give the student experience first, and then the vocabulary to express what they know. Give the student a concrete experience and say, here's why we use this sort of mathematics in this situation. It's not just, I always felt mathematics, the way we taught it in the United States, was this very odd and strange puzzle that was very evil And the teacher never told me why. I felt the teacher never understood why. Why do we have to learn this? I don't know. It's in the book. It's required for graduation, all these sorts of answers. But I never got answers like, oh, here, we can use this to make a map. We can use this map to compare the size of the Earth to the size of the moon. We can use these ideas to measure the orbital motion of the moon. We can actually do this with simple materials. You can do it yourself in your own backyard. You can go out in the schoolyard in your city, anywhere, doesn't matter. Light pollution doesn't matter. And you can do these measurements and calculations of the moon's orbital motion. And to be able to say to someone, now you've measured the moon in motion around the Earth in space, almost 400,000 kilometers away, and you're measuring it here with simple tools and getting accurate results. I'm sure we've all heard of the great conjunction of Jupiter and Saturn, right? If you follow any kind of scientific websites or social media sites, there's been all this talk. Oh, the great conjunction, Jupiter and Saturn, closest in 800 years. How many websites have told you, go out and measure with a ruler at arm's length, because 1 centimeter on a ruler at arm's length is approximately 1 degree, and measure and track the progress as the two planets converge? I've not seen that anywhere. And yet, it doesn't require fascinating equipment. It requires a ruler and a clock or a calendar. How fast are these two approaching? How many degrees per day are they covering as they converge? How many websites have told you, here's an opportunity to measure planets in motion in space? None, because we don't teach science that way. We teach astronomy as something that's far away and really big, and it's so big we can't teach it to you, and it's so far away we can't imagine it, and you have to have the Hubble telescope to do measurements like this. That's nonsense. We can do these measurements with our students today with very simple materials, and it doesn't have to cost a great deal. It can be very inexpensive, and that doesn't mean it's poor science. That doesn't mean it's inaccurate or ineffective. It can be very accurate, effective. It can be conceptually very powerful. Once a student has done these measurements and then they go to the textbook, then they're bringing knowledge to the textbook, and it means more to them. This is the exact idea of making a model of the lunar surface in clay. Oh, model the Maria, model the mountains, model the ray systems, model the central mountain craters, model the ejecta patterns. Now, measure them. Measure their area, circumference, perimeter. Use water and drip water into the craters. Measure the crater volume as an approximation of energy. Look at the way your clay flows. Oh, look, I'm having a lava flow that's breaking out of one area and flowing into another crater. Do these things happen on the moon? This is my hypothesis. Now when I go to the eyepiece, I'm actually doing an experiment. I'm comparing my hypothesis in clay to my data through the eyepiece. I'm not just looking at the moon, I'm doing real science. And that is powerful, it's effective, and my friends, it is affordable. You don't have to live in a very wealthy area or have very wealthy backers or very wealthy citizens in your town or locality supporting your school. That's not true. Science isn't just for the wealthy. If you think about the history of science across hundreds of years, how many great discoveries were made by men and women with simple materials, doing experiments on their own. Newton did it, Copernicus did it, Galileo did it, and yet today we think, oh, the Hubble telescope costs $1 billion. Oh, this observatory being built in Chile in the Atacama Desert costs $2 billion. And these space missions to Mars cost hundreds of millions of dollars. And the student tends to think of science as something that requires enormous resources that individuals cannot afford unless you're someone like Bill Gates or Elon Musk. It takes governments, it takes billions, and it's not true. It's not true. Your students can do these observations. Your students can do these activities. Your students can make these measurements. They can make a model. They can make an hypothesis. They can go ahead and compare their model to what they see in the sky. They can gain an appreciation that all models have their weaknesses. Oh, here's the Earth and the Moon, and they're the same size. That's not true. Oh, well, here's a model that shows how the moon's face has changed from new to crescent. Oh, here it's gibbous. Now it's full. Now it's waning, and so on. Well, but the fact of the matter is that when we observe this in the sky, that this crescent rotates as it moves across the sky. We can understand the limitations of scientific models. We can understand the limitations of science as a process. But we cannot teach science as a human activity, as a process, unless our students engage in that process. This is like teaching someone to play the violin by telling them, read this exciting book about violin playing and famous violinists. Do you get to play the violin? Do I get to try it, teacher? Oh, no. That's too expensive. It's too remote. It's too far away. We couldn't possibly do that. Read more about violin playing. Now you're a violinist. And it's a lie. And we tell students, watch YouTube videos. Read this textbook. Do these abstruse calculations. There, now you know what science is. Now you're a scientist. And it's not true. It should be the way we teach science, but unfortunately, it's usually not. My plea to you as we summarize and we come to the end of these 3 series of exciting lectures is simply this. And I'm going to switch back and talk to you face to face now. Here we are. So my plea to you, my friends, is that in your own school, in your classroom, in your home with your own children, please do not present science and mathematics as something removed from reality. Don't teach your students that science is something for people at big universities who have fancy laboratories and lots of money and powerful, wealthy backers. No, science is for everyone. Science is a process that we engage in as human beings. Science is a process that has limitations. When we come up with an hypothesis, and whether that's about vaccines or climate change or the origin of life, or is there life underground on Mars, or any of 100 other topics that you can think of, these are not abstruse things. This is a process done by human beings. And we can have students say, can we model the phases of the moon? Yes. Is our model perfect? No. Where's the model lacking? What is it lacking? What needs to change to make it more accurate? And as they struggle to make a more accurate scientific model, and they change from, let's represent phases of the moon with simple flat pieces of clay, or in this case, salt dough, and let's improve our model and make our moon into a sphere. And, let's put the Earth in our model. Oh, wait, they're the same size. And we get to realize that our model is never perfect, that science is a process. Science is not, contrary to much of what you see on the internet and the news services, science is not something we do to prove we are right. Science is a process we engage in to become more right. We don't do it to prove we are smart. We engage in science to gather more knowledge and more understanding. And we cannot teach that if our students do not engage in this process. Our students must engage in this process. Sadly, in the United States, and I suspect in many places around the world, science is taught as, oh, here's what's true. Look, it's in the book. This scientist has said so. And we teach it as a collection of facts. We don't teach it as a process done by human beings. So if I could make one last plea to you, please try some low-cost methods. Engage your students in doing actual scientific activities. Go ahead, start them out. Here's the phases of the moon. Here's a better model. And then say, all right, now it's time to go out at night and look at the moon. Do some real science. Make your own observations. What do you find? Where's your model lacking? This will do more to advance the cause of science worldwide than any number of textbooks and videos could ever do. So I thank you. I thank you for coming, for listening, for being my friend with me and taking this adventure with me. And I would be happy to take some questions before we go. We seem to have an echo.
Yeah. I think it's fine now, right? Sorry.
That's all right.
Thank you, Daniel, so much for that lovely session. And that's true. I fully agree with you that the students have to do science to truly appreciate the fun of it. Otherwise, they will, never be able to enjoy what we enjoy about it. So I really love that idea of yours. And I do hope, and I'm sure that with the demos you showed us, a lot of the teachers, etc., would be able to plan up some activities, right? So let's keep it open now for questions. So I welcome questions from the participants.
Yes, I'm hoping to hear some questions from you verbally, or if you want to type them.
You can unmute yourself and ask a question. Come on, let's ask some questions.
I see people saying thank you, and I appreciate that.
Yeah, there are many thank yous, but.
And certainly the Astronomy for Educators Facebook page, that's open, and you're welcome to post questions, or if you have comments or reviews of the lectures or the book and you would like to post them there, I would very much like to hear them. And sometimes I know when I'm in a lecture and I'm walking out of the building and I think, I should have asked this question. This often happens to students everywhere. So if you have those questions about science teaching, certainly I would be happy to answer them. You can post them on the Astronomy for Educators Facebook page. What kind of activities could be done with 16 to 18-year-olds as part of Astronomy Club? I think you would find that all of these activities would work very nicely for an astronomy club. They're inexpensive, and you can get the Astronomy for Educators book online for free. The students can get it as well. The instructions are all there, and there are questions there. And for each activity, there's also suggestions. Now that you've done this activity, here's some observations you can do yourself. And I think that would be perfect for a club. There's a question about what is a geodesic line? Geodesic line is perpendicular to a gravitational field. That's more of a term that you find in relativity than in astronomy. The idea of curved space-time. There's the illustration of the ant crawling across the apple. The ant sees itself as traveling perfectly flat all the time because it's always perpendicular. Gravity is always perpendicular to the surface, but in fact, the surface it's moving over is warped. And thus it is with space-time, and it's the curvature of space-time which creates orbits, but that's kind of beyond the scope of our presentation here. We get, a nice idea to engage our students with some hands-on basic astronomy activities. Yes, and I must tell you, I I developed all these in my classroom over 35 years teaching astronomy, and I developed them because I couldn't afford equipment. I had very little money in my school systems, and so I had to find a way. And the book is really the result of 35 years of trial and error. How can we make a model? How can we make it more effective? Well, that didn't work. Let's try something different. And so the 36 activities from the book are all, they're the success stories, and they're the processes that came to be effective later on. I'm hoping we have a few more questions before we go today.
Yeah. They are just thank yous, but I need questions.
Yeah, it's funny when I speak with my students and I say, who has questions? And no one raises their hand. And I say, aha, I have taught you to a standstill. I've taught you everything you need, and now there are no questions. And of course, I say that as a joke, but oh my goodness. Are you seeing any questions on the YouTube channel?
Oh, I'll check that. I'll just check that.
What do you think? Why do you think teachers often shy away from doing practical sessions? They feel very comfortable doing theory, but practicals probably it involves a lot of work.
That's a brilliant question.
Chances when it often fails when you are demonstrating.
That's a brilliant question. I think it has much to do with the way the teachers were taught science themselves. I think many of us who teach science, especially to younger children, are not scientists by training. And so you get these teachers who didn't take a great number of science and mathematics classes, and maybe when they had them, they didn't enjoy them. And so they get into the class with the younger students and, oh, well, science is hard. I didn't like it. I don't know how to do this. I don't have the money. And they have the idea that science laboratory activities have to be the way they experience them at the university. Here we have a very fancy laboratory. We have very nice equipment. Well, now I'm at my local school. I don't have that kind of funding. I don't have that kind of resources. And so I can't do this. The truth is you can. And that's the entire idea behind the Astronomy for Educators program and the initiative that I'm trying to get more universities to train their teachers in this low-cost, hands-on manner, rather than training teachers in a very abstract manner. I want more universities to teach young educators to do science in a low-cost, hands-on, experience-first methodology. I think this would make science more fun for everyone. Students would enjoy it, teachers would enjoy it, and I think it would, one of the problems we have in the United States, we refer to this as the STEM pipeline. We start out with young children, perhaps 8, 10, 12 years old. They all enjoy science. This is fun. Oh, look, we get to do things. But by the time they are 16, 17, 18, 20 years old, fewer and fewer students want to continue with science. And I think if we start teaching our teachers, training our teachers, and then teaching our young children science as an activity where it's something fun we do, it's an activity, not a list of vocabulary, I think we will keep more students in the STEM professions. And I think that will help with poverty because STEM careers pay well. And I think there's an economic purpose to school. Part of our job as teachers is to make our students employable. Because when we raise a student up through education to a better paying career, we impact that child's children 20, 30 years from now. We impact many generations, not just one. And I think that's crucial too. Other questions, my friends? I'm not seeing very many. I'm hoping that you will go to my Facebook page, Astronomy for Educators, that you will leave a comment, that you will leave a review on the book. If you have questions about how do I teach this activity or that activity, I'm hoping that you will post them there. And I check that every day, and I'll be happy to answer questions. And my email, astronomyforeducators@gmail.com. If you have a question about how do I teach astronomy in my school, how can I do this activity with my students, I would very much encourage you to reach out and contact me. I would be very happy to talk to you. Share the web address so other colleagues and teachers and parents and even students and astronomy club members can download the book for free. That's why the university provides it that way for you. And I want to thank you, Dr. Hassan and Dr. Hassan, both of you, for inviting me. This has been extremely exciting for me to be able to reach out and contact teachers in your country and around the world through Srishti Astronomy, because this is my mission. I'm not doing this to become famous or to make money. Certainly neither of those things are happening, but I am doing this to improve teaching worldwide and make astronomy and space science education more powerful, more engaging, more affordable, so it's accessible to more people. And you have given me a platform and an opportunity to speak to teachers across your country, and I'm sure many others will see these presentations on YouTube, and I must thank you both from the bottom of my heart. It's been a lovely experience, and I've really enjoyed it. Thank you.
It has been a lovely experience for us as well to interact with you. And I hope that after a small gap, we'll invite you again. We'll give them some time to get into your book, try things out, and then after some time, we'll bother you again. Invite you.
Yes, I would very much like that. And if more people see this on YouTube and you get requests, perhaps we could come back in a few months' time and do some other activities. I would enjoy making this a regular, maybe a semi-annual thing where we come back once a semester for a couple of presentations and do some more activities and more low-cost science. And if we do it in the fall, then I think, and COVID goes away, please, then it would be very interesting because we could do this as an activity with my astronomy education students. I have in my program about 25 students every fall who are young teachers who are coming to learn. And my class is usually at 8 in the morning, which is 8 in the evening, your time, 8:30. So it might be possible for you to join me in my classroom where I'm teaching young educators to teach astronomy. That might be a fun thing to do through Zoom as well. So there are many exciting things, and I'm hoping we will this relationship will continue for many years to come.
Yeah, so yeah, we also highly appreciate all the efforts you are taking. That's really very good. And to spread the message to teachers all over the world is also a very good thing. But just to let you know, we were actually doing an initiative in India called the Hockey Stick Challenge, where we've been actually, we showed people how to make a cross staff with which they can actually measure the angular distance between Jupiter and Saturn. So we actually have a bunch of students who have been actually contributing the values they've been getting every day. So we hope to get our hockey stick plot by the, post conjunction too. So we've actually been trying to do this business of getting people to measure, because like you said, they have to be doing it so that
yes, I applaud your efforts. This is wonderful. This is wonderful, and a chance for you to get people all across your country engaged in the process of doing astronomy, doing science.
Yeah, so what we actually did is all over the country, we did it in some 15 languages. We made short YouTube videos, and in 15 different Indian languages, we told people about what they should be doing. And we also encouraged people to design their own cross staff We showed them some cross staffs, and then, you know, people have designed cross staffs which are quite interesting. The way they've actually made it, it's a nice thing. And but yes, more efforts are obviously required, and we look forward to that. I would like all the participants to switch on their cameras for a minute, and we can probably see everyone, because I think that would be a nice experience for you, because you've not seen the people you were talking to.
No, I haven't.
Yeah. So
Yes, that would be very exciting.
Get their cameras on. Let us all look at y'all, and please, everyone, switch on your videos, your cameras. Let's have a look at everyone so that we can at least say hello.
This is marvelous. And while you're doing that, I would like to invite you, because my book is an open resource text, you are welcome to translate any of the parts of the book or the activities into your own language. And if you do that, I would very much appreciate if you could email me a PDF showing this in different languages. This would be very exciting. It shows that the book is becoming, tell me in English, of course, what section, because I have no facility in Indian languages at all, sorry. But if you say, oh, this is the activity for making the planetary models, or this is the activity for doing different things, and here it is in our own language, I would love to see that. So, and I'm seeing people turning on their videos now, some of you, and it's very nice to see you and to tell you good evening. It's just becoming morning here, as I am half a world away, but in my heart, I'm with you 100%.
Yeah. I maybe a few people are okay. Yeah. So thanks a lot, Daniel. And let's not say a big goodbye, because we do hope that we will, we know, rather we don't hope, we do know that we are going to meet again. So till we meet again, let's say that.
Thank you very much.
Thank you.
Bye-bye.
Bye-bye, everyone. Don't forget to leave a comment on the Astronomy for Educators page on Facebook, please, because that's important for me.
I have shared on the chat window. I've shared the Facebook page.
Thank you.
As well
Thank you very much.
The feedback form, which will be what is required for you to get your certificate. So I request everybody to fill the feedback form, as well as go to the Facebook page, which
Outstanding.
has details.
Outstanding. Thank you very much, and I'll leave you now, and thank you very much. Bye-bye.
1 second.
Ma'am.
Oh, 1 second, 1 second.
One question?
No, ma'am, feedback form में session did you attend में एक ही option attend fill हो रहा है ना?
Okay, I'll check it. मैं वो check it. वो तीनों है options. Yeah, okay, that's fine. Okay, all the options are there. 1 sec. Some more pictures are coming up, so let's take some more pictures. Yeah, 1 second. I'll just try to. I'll take a screenshot, but the problem is not many people have switched on their videos. So
No. It may be a local bandwidth problem too. If people don't have good internet.
Problem that
it's typical. I can see a couple of friends here now, and that's wonderful.
Yeah.
So I'm hoping you've all enjoyed the presentations.
Yes. So see you. Bye-bye.
Okay. Bye-bye now.
Yes. Bye-bye.
Thank you.
Thank you.